Okay, so let's have a look at this problem here. It's the one we actually started earlier with where we'd solved that based upon the combination of this rotational input, this rotational output, and the 4-inch offset, that we need the diameter of the pinions to be 2 inches, and we need the diameter of the gears to be 6 inches. And obviously that goes for both sides as well. In addition, we want this thing to be transmitting 6 horsepower. The input is going to be equivalent to a light shock condition. The machine it's connected to is a medium shock. We've got bearings of ordinary precision requirements. Overall life expectancy of 10 to the 7 cycles, and a reliability of 99%. And then we want to have a safety factor of 1.2. So that'll be for both the surface fatigue and the bending fatigue, or the volume strength. Operating temperature less than 160 degrees Fahrenheit. So again, we're operating, it's not hot enough that that's going to affect things. And we're making them out of steel with it's a precision shaved and ground. So first step, we want to determine the geometric characteristics of each gear. So I'm going to skip ahead here a bit. So I want to, we're going to go to the avoid interference. Based upon that, we've got this formula down here, which gives us the minimum number of teeth in the pinion in order to avoid interference. So if we got the k here is equal to 1, based upon that note, we're assuming full gear teeth, not stub teeth. If we have our gear ratio of 3, so that's 3, that's 1, sine 20, that's a sine 20 as well, sine 20 squared. Again, the gear ratio here is 3, gear ratio that's squared here is 3, 3, so on and so forth. Plug that into the calculator. I've already done it a few times. You can just trust me on it, or you can pause and plug it in yourself, and that'll get 14.9, which of course we need to round up to 15 because we can't have a non-integer number of teeth. So that's going to be the minimum number of teeth on the pinion. So as for what we're actually going to be using for the number of teeth, that's where we go back to the geometric characteristics. So what we are worried about here, which that's what we want. So what we want is we need to pick a pitch, basically. So again, pitch is equal to the number of teeth divided by the diameter. So we need to have at least 15 teeth, which means that the pitch times the diameter needs to be at least, the pitch needs to be at least 15 divided by the diameter. So the diameter is 2, so 15 divided by 2, 7.5. So again, if we go back up to this chart right here, we see that, all right, 8 is a reasonable, we can likely find 8. 8 or 10 would probably be suitable. We'll stick with the 8 value for now. So that our pitch, P, is equal to 8 per inch. So if P is 8 per inch, the other aspect of the geometry of the gear that we need to find out is the width of the gear. So the face width of the gear, again, typically varies from 9 over P to 14 over P. So we can pick something in the middle. We can pick something on the high end if we want. Um, let's and again, what you actually decide will also depend upon what sort of gears you can get from your supplier. Assuming you probably don't want to be having these custom made. So if you can get something that's suitable in house, like off the shelf, then that'd be great. But let's for the time being assume we're gonna go fairly wide. Just kind of share the load a bit better. So yeah, let's go with a B of 14 over P. So 14 over 8 per inch. That'll give us 1.75 inches. Alright, so our B's 1.75 inches. The other aspects of the geometry kind of follow from what we've seen already. So we are going to be looking at the addendum. That's a function of the P. The dedendum is also a function of the P. The base circle is a function of the T. So for the time being, our addendum size is equal to 1 over P. So that's 1 over 8 per inch. So 0.1125. Sorry, no. 0.125, not 1125. My bad. I should have known better than to trust my shoddy memory about what 1 over 8 is. Why did it? And then I put 8 there. 125. There we go. So that's the size of our addendum, which we're going to have to use when we look at our contact ratio. So we're looking at our contact ratio. I'm just going to go and scroll down and have a look at what our formula is for that. So we're going to be using this to calculate that, which I'm just going to kind of cut and paste into here. So the values that we're working with, we need the radius of the addendum for the pinion and the gear, and the radius of the base for the base circle for the pinion and the gear. So the radius of the addendum for either of them is just the radius of the pitch circle plus the addendum. So the addendum is the same size for both, and then the diameter of the pitch circle is 1 inch for the pinion and 3 inches for the gear. So our RAP is going to be 1.125 inches. Our RAG is going to be equal to 3.125 inches. Our radius of the base circle for the pinion is going to be just based upon half of this value here, the half of the diameter times the cos of the pressure angle. So 1 inch times cos of the pressure angle, that gives us 0.9397 inches. And then since this value here varies directly with the diameter, we know that the radius of the base circle for the gear just needs to be 3 times that. So 2.819 inches. So other values here, so we've got this C, that's just based upon the offset between the two shafts. So the center line to center line offset was 4 inches. Obviously the pressure angles are all 20 degrees. So let's start plugging in numbers here. So we've got this term here, 1.125 squared minus 0.9397 squared. Take the square root of that. That term there is 6.619 inches. This term here next to it, we got the 3.125 squared minus 2.819 squared, and then take the square root of that. That gives us 1.349 inches. And then 4 times the sine of 20 degrees gives us 1.368 inches. Then this term here at the bottom, pi divided by 8 per inch times cosine of 20. That gives us 0.369 inches. So add the stuff on the top together. I'll subtract the last term because it's negative. That's 0.6 divided by 0.369. That gives us a contact ratio of 1.62. Sorry, rounds to 1.63. So that is perfectly adequate. Okay, so next up, so we got 1 done, we got 2 done, we got 3 done. Recommendation on the volume and surface strengths of each element. So first off, let's figure out what the stresses are. So if we recall that our stress levels are going to be based upon this formula right here. So first off, what is our FT? The the transverse portion of the force, or the force causing the torque. I'm not sure if it's if that's T is for torque or transverse. Whatever, it doesn't really. No, I'm not too picky, but what it actually means, as long as you know what it is. So can figure that out based upon the fact that we know what the power is. So the transmitted power, again, we're missing the work rate. Transmitted power is equal to that Ft times the velocity divided by 33,000. So if Ft is in feet, is in pounds, and V is in feet per minute, and again we calculate our the V just with pi times the diameter in feet times the RPM. So let's get that V1 going first. So again we're worried about what's going on in the pinion. I'd also like to specify that we're worried about what's going on this pinion right here. So that's going to be the weak factor, not this one, because this is the one that sees the higher torque. The one on the right sees the higher torque. This one here is the higher speed. So the higher torque results in higher stresses. Higher stresses leads to fatigue failure. So what we want to do is figure out what our V is based upon the rotational speed of 400 RPM. So our V is going to be equal to 400 RPM times pi times the diameter of the times our pitch diameter in feet. So that is going to be 2 inches divided by 12 inch per foot. So inches cancel out, we get feet on the top. So 400 times pi times 2 divided by 12. So that there is 209 feet per minute is our kind of our velocity there. Actually, that's a bit off the screen here. I'll rewrite that. Okay, so that's our velocity. And then the power rate is equal to the force times the velocity divided by 33,000 feet pounds per minute. So yeah, 33,000 feet pounds per minute, or 550 pound feet per second is what a horsepower is. So 33,000 feet pounds per minute per horsepower. That's that conversion factor right there. So if we want to know what our FT is, we basically just need to multiply out this conversion factor and plug in our values for the work being done. So we have 6 horsepower times 33,000. Oh, here, I'll scroll up a little bit. Times 33,000 feet pounds per minute per horsepower. Obviously, the horsepower is cancel out, and then we need to divide by our V as well. So divide by the 209 feet per minute. So that cancels these out. And we are left with FT is equal to 6 times 33,000 divided by 209. That gives us an FT of 947 pounds. Pound force. Okay, so we got that. We got the force. We know what the pitch is. We know what the B is. So we need to know what this J is next. So that J there is the corrected geometry factor. So basically taking that Lewis form factor and correcting it for stress concentration effects. So that is a function of the number of teeth, and is in the gear that we're looking at. Again, in this case, we're looking at the pinion, number of teeth in the pinion, and it is a function of the number of teeth it's mating with. If the number of teeth gets high enough, it doesn't in this case. So in this case, we're at, I like to draw a straight line for that. So we're at 16 is the number of teeth in our pinion, which means that our line intersects right about there. That to me looks to be about 2.27. 0.27 is our value for J. And then KV, KO, KM. So our KV, that's our dynamic factor. That's based upon the surface quality and the speed at the pitch diameter. So looking at this graph here, I had said that we are looking at a precision shaved and ground gear. So that's this line right here. And we're looking at a pitch line velocity that's 209. So that's fairly low. So I'm going to zoom in a bit here. So, sorry, 209. Did I say 2000? I forget. Yeah, so here's 500, 250, 200 should be right about there. 209 should be right about there. So our intersection right there. What do you think? 1.2? 1.15 maybe? Let's go 1.2. We'll err on the side of caution. So that's 1.2. Our KV. Next thing we want is our KO. So overload factor. So the KO is a function of kind of how much pulsing you get in the torque that is kind of being applied to the gears based upon the shock in the power source and the shock in the machinery. So in this case, we had said it was a light shock power source and a moderate shock machine that's being driven. So we got a KO of 1.5. 1.5. And then our KM. So our Km there is a function of the load distribution. How accurately is this mounted? So it is said it was an ordinary mounting condition. So if we look at our chart, at our graph here, I'm going to say that doesn't necessarily count as, accurate mounting or small bearing clearances or minimum deflection. We're not necessarily getting that, but we're still getting full contact across the full face. So it's not bad enough that less than full face contact exists. Otherwise, they would have mentioned it. So we are looking at this row here. And the face width is 1.75 inches. So we're looking at this column here. So our KM is 1.6. 0.6. So now we got that. Now we can solve for what our stress level is. So our stress is going to be equal to our FT, 947 pounds force, times the P. So 8 per inch divided by our face width, so 1.75 inches, times our geometry form factor, the J of 0.27, and then times our KV, KO, and KM, times 1.2 times 1.5 times 1.6. That is a terrible looking 6. Let's see here. There we go. So what does that give us? 947 times 8 times 1.2 times 1.5 times 1.6 divided by 1.75 and 0.27. It gives us syntax error. Yeah, let's try that again. Alright, so our stress level here, that's going to be equal to 47 KSI. So that's the stress that we're looking at. Obviously, we need to compare that to some sort of strength. So we use this nice formula right here to determine our strength. So I'm just going to go ahead and screenshot that. So the stuff we don't know here is our SNs, because we're trying to find out what sort of materials we need. We know it's some sort of steel, but we don't know kind of what sort of heat treatments we need to do to it, or what alloy we need to use, or what have you. So that is unknown. Our CL is equal to 1, because CL always equals to 1 in this case. Our CG in this case is equal to 1, because the gradient factor is equal to 1 if you have a P, your pitch, that is less than 5 per inch. Sorry, greater than 5 per inch. So we are at 8. So we're good to go there. So that's also equal to 1. Our CS, we need to go to the charts for that. So for that, we're going to go to our handy dandy juveniles. Going to go to chapter 8. And let's see here. And we're just going to pretend I didn't draw over that previously. There we go. Let's just screenshot that. Stick it in here. So, we are assuming here that we are working with a fine ground or commercially polished situation at the root tip. We're not talking mirror polished. No one's mirror polishing the inside of gear teeth, but fine ground and commercially polished is completely reasonable. And we did specify at the beginning that it's precision shaved and ground. Is how it's worded up at the top there. So let us. So basically, we know that we kind of need to make a guess about what sort of hardness we might need for this, because we're using this value to calculate the hardness, but it's a function of the hardness. Or the tensile strength. Essentially, for gears, you're often talking about Brinell hardness numbers instead of necessarily the ultimate strengths. Because you can measure that on a gear. You can do a Brinell hardness test on the gear. You can't necessarily do a tensile test with the gear. So we can often get the hardness easily, and fortunately Brinell's hardness very strongly correlates to the ultimate strength, and it's usually fairly reasonable to take your Brinell hardness number, divide it by 2, and that gives you your ultimate strength. So we need to make an estimate about what we might be expecting here for this to look at our CS. So yeah, it's our CS is going to vary between 0.9 and 0.7, depending upon where along that axis we are. I don't know. Is it unreasonable to kind of assume a worst case scenario, or is it unreasonable to assume a best case scenario? How about for the time being, we put it somewhere in the middle? How about we just assume that we're working with the 0.8 that occurs at a Brinell's hardness number of 440. And then if we end up with a value for the strength required that is substantially higher than that, then we probably need to go revisit that because we guessed too low on our CS. If we end up calculating a Brinell's hardness number that is a required Brinell's hardness number that's smaller than that, then we underestimated our CS, which means that we kind of made too conservative an assumption, which, okay, so be it. Unless that would substantially ramp up the costs, then you might just accept it, or you might spend the 10 minutes it might take to redo your calculations based upon a new iteration. But anyways, for now, let's use the CS of 0.8. And then we got our KR here. Again, I don't know why when they switched to gears, they decided to start using KR instead of CR. They used the KR in the strength for bending. And then yeah, I don't know why. So we were talking 99%. So we're looking at a KR of 0.814. CT, the temperature effect. The temperature is, we were told, would stay below 160 degrees Fahrenheit, so that's going to be equal to 1. And then the MS, the mean strength effect. So again, that's based upon whether or not we have this thing going up and down in stress, or whether or not we have this thing just going up. Oh, yeah. So in this instance, because this is not an idler gear, this is all these gears involved, are only going to be seeing force on one side applied to one side of the gear. So we're working with a KMS of 1.4. 1.4. So then we can figure out what our strength is in terms of Sn prime. Sn prime times 0.8 times 0.814 times 1.4. So that gives us an S that is equal to 0.91 Sn prime. So again, like I said, we want to kind of get this in terms of your Brinell's hardness number. So again, Sn prime is typically equal to 0.5 over SU, and then SU is typically equal to 0.5 of the Brinell's hardness number when measured in KSI. So our S value here is going to be equal to 0.94 times 0.25 times the Brinell's hardness number. So that's going to be our strength that we would need. And again, what is that? 0.91 times 0.24, 2275 BHN. So that strength divided by our safety factor of 1.2 needs to be greater than or equal to the stress level that we're seeing of the 46 KSI. Greater than or equal to 46 KSI. So if we just solve for the Brinell's hardness number, 46 times 1.2 divided by 0.2275, that means that we need to have a Brinell's hardness number that is greater than or equal to 243 when we round it, which is reasonably obtainable for most steels. So that'll be in terms of the fatigue crack growth damage. We're also worried about the surface fatigue. So this is damage, this is cracks growing like this that then cause your gear tooth to break off completely. We're also worried about basically erosion that's going on kind of on the face that comes into contact with the other gear. So what do we do for that? We got this nice formula right here. So I'm going to copy and paste that. So some of the stuff we know already. The FT, that was FT was 947 pounds. KV, KO, KM. That's these right here. So 1.2 times 1.5 times 1.6. All those together is 2.88. Our B here, 1.75 inches. Our diameter of the pinion here, 2 inches. So we need to know what our CP is, and we need to know what our I is. So I, that's given here, and that's in terms of the radius of the gear ratio. So the diameter of the gear divided by the diameter of the pinion, or the number of teeth in the gear divided by the number of teeth in the pinion. That R is 3 in this case. So this term here is 3 over 4. These two terms here combined, 3 over 8, times the sine of 20 degrees times the cosine of 20 degrees. So sine 20 times cos 20 times 3 over 8. That gives us an I is equal to 0.121. So that's our I. The CP term here is a function of the materials in the pinion and the gear. So in this case, both pinion and gear are made of steel. Not that one, because that's the metric table. So the value that we're looking for is the 2300 root psi. So let's throw everything together here. 2300 root psi times square root of 947 pounds divided by 1.75 inches times 2 inches times 0.121, and then this term here, all these three terms here combined to 2.88. So 947 times 2.88 divided by 1.75 times 2 times 0.121. So everything there, and then take the square root. It ends up being 80.2 watt pounds per square inch, and then square root. So when we multiply that out by the square root on the outside here, the result that we get in the end is in psi. So 80.2 times the 2300. This gives us a contact stress of 184 psi. Sorry, KSI. 184,000 pounds per square inch. Okay, so obviously we need to compare that stress level to some sort of strength. So the strength value we're using is this here. So we need our SFE, we need our LI, and we need our CR. So our fatigue life correction factor, based upon a desired number of fatigue cycles of 10 to the 7, which is what the problem asks for, is 1. So our CLI is 1. The reliability factor used for what am I trying to say here? The reliability factor used for surface fatigue damage at 99% reliability, which is what we asked for, is 1. So 1, 1, therefore our SH is equal to SFE. What does SFE equal to? So that depends upon the material. That's a material property. And for steel, it's a function here of our Brinell's hardness number. So 0.4 times the Brinell's hardness number minus 10. 0.4 times the Brinell's hardness number minus 10. And that'll be in KSI. So, as per usual, we need to involve the safety factor as well. So again, our strength level divided by our factor of safety needs to be larger than our stress level. So if we want to ensure that this thing is safe, we need a Brinell's hardness number such that 0.4 times the Brinell's hardness number minus 10 KSI is greater than 184 KSI times the safety factor of 1.2. So 184 times 1.2, that gives us 220.8 plus the 10 KSI to move over from the other side, divide by 0.4. That gives us a required Brinell's hardness number on the surface of the material that needs to be greater than 577. So again, that is certainly not as easily attainable as the Brinell's hardness number of 243 that we required in order to have a safe operation in terms of, what am I trying to say, in terms of the crack growth at the root. But this can be obtained through, it needs to be obtained through heat treatment of the entire gear. whereas the Brindle's hardness number for the surface fatigue, that's based upon just the strength at the surface. So if we want to do that, we can use some sort of treatment that only targets the surface. It doesn't necessarily need to penetrate deep. So if we use something like a case hardening or what have you, then we would be able to use that. So yeah, those are basically kind of the two material requirements that we would need to have for the Brinell's hardness number of the pinion. Uh, the and that's again for the limiting factor here is based upon yeah, that is based upon, let me zoom over here. That's based upon this pinion here, again to reiterate, because the stresses it sees are higher, as opposed to this pinion here, where it's seeing more rotations, certainly, but the stresses aren't nearly as high. So as a result, and again, we're designing for infinite life. Oh, well, sorry, we're designing for 10 to the 7 cycles. So if we drop the stresses that would be seen by 3 because the torque's 1/3, as a result, we expect the fact that this thing's seeing 3 times as many rotations is not nearly overcompensated by by the fact that its stress level is so much higher. So we're worried about that one here. And then obviously similar for the gear. It's less critical for the gear, but that at the very least the gear itself will be seeing stress levels that are at least on the same order. I mean, it's going to be slightly less because primarily when we go to look at the J factor for the gear, when we're looking at the bending stress levels, the force is the same, the pitch is the same, the width is the same, all this stuff is the same except for the J, because the J, again, you'll recall, is a function of the number of gear teeth. So for the pinion, stop doing that. Okay. So for the pinion, we were over here at 16. So 16 times 3, 48. So here we'll be looking at a line right about there. So that would be a J factor of 0.39, I guess. So essentially, we can expect the bending stress that we would see to be reduced by a factor of 1.4 on the bending stress. And then similarly, so that comes in factor for the bending. If we look at the stresses involved for the surface contact, it is going to be seeing the same stress levels because nothing here changes with the when you switch from the gear to the pinion at all. Contact stress is going to be the same for both as long as they're the same material. And then obviously the the main difference here would be that the gear doesn't need to rotate as much. So for every 1 rotation that the gear makes, the pinion's making 3. So it's not designing for its CL here isn't for a number of cycles of 10 to the 7, it's designing for 3.3 times 10 to the 6. So, right about, well, probably hard to. I'm not very good at kind of figuring out we're relying upon a log graph, but I think that might be kind of about here-ish. So, yeah, 0.105. So the strength, basically the apparent strength of your material would be a bit larger because it doesn't need to see as many rotations. But yeah, that's about that.